Morning, everybody. Happy Wednesday. Got a new camera angle today, so I don't disappear out of sight every time I write something down. Good morning, Joey. Do you guys have like a morning routine? Like, do you like get your cup of coffee, come sit down at your computer, or do you just literally wake up? You're like, oh, I'll go to class today. I do. I imagine most of you guys are probably doing your work on a laptop. Do you guys have desks? Well, I guess if you're in the dorm rooms, you have a desk. At home, maybe not. What kind of coffee do you like, Joey? You like dark roast, medium roast, light roast, straight black, with a little... Light roast with milk and sugar. Sounds delicious. Actually, not really. I don't like coffee. Morning, other Joey. Tea is good. I have a friend who is doing some work over in the UK, and she learned how to make a proper British cup of tea. And she was amazed that they brew the tea for like literally 2 seconds. You like dip the tea bag in, that's it. And then you take it out. And she's like, this doesn't even taste like tea. It's like mildly flavored water. See, back to the desk conversation. I saw some people taking the exam on like a windowsill on their beds. So I'm just curious to see how you guys are surviving. So that it... I have to put my phone on my keyboard. Oh, okay. Yeah, just the limited amount of space. I made my desk out of an old closet door. We took out a bunch of the closet doors when we moved in. So I made my desk. I went out and I bought some 2x4s, screwed them together to make legs, and put my desk on, or made my desk that way. It's actually kind of nice. Yeah. I used to wake up at 5:30, and I don't anymore. I wake up at 6:30. Not having to commute and drive somewhere actually saves a decent amount of time. Like, can you imagine not having to take the bus to school? Looking at high school. Okay, we got about 1 more minute until class starts. Are there any questions on anything? You guys got your midterm grades yesterday, so that might be exciting, might not be exciting, depending on how you did and how you hoped you did. I will talk to the other instructors tomorrow. We have our meeting tomorrow, and see what it looks like to give solutions. I mean, there's multiple ways to do different problems. I don't think we typically post solutions to the midterm. You can always email me and ask me if I have if I can give you some more feedback on the midterm. I can do that to some point. But I will talk to the other instructors and let you know in terms of what type of solutions can be posted for the questions. I can also see if you guys can have access to the questions as well. Okay, Joey's question, will the final be structured by the midterm? So that's a good question, Joey, especially moving forward. The final will be structured in terms of how the midterm was delivered. So you're going to have a question that you need to solve, a question you need to solve. It's going to be randomly chosen between a group of 4 or 5, whatever. And you'll have probably 6 or 7 questions to answer. However, the final is going to be mostly on linear algebra. There's going to be very limited MATLAB that you're going to have to do for your exam questions. You will still have access to MATLAB. You can still technically check your solutions and everything. You will still have a limited amount of time to do everything. But it's going to be linear algebra stuff. So if you're looking forward and trying to improve your grade in this class, you want to make sure to do the programming project. So that's still really important to do because it's 15% of your grade. Even if you don't do very well on it, like 50% of 15 is much better than 0% of 15. But I mean, you should be able to do a decent amount of the project. You still have like 3 weeks to do it. So make sure you're working on it. Also, make sure you're focusing on the linear algebra stuff for your homework. The linear algebra stuff, it's just practice. When we get to week D, there's some important theoretical concepts that we're going to focus on, but it's really just practice. So make sure you're doing your homework. If you have time, do an extra problem. They just take time. Joey, yes, the final will also be open book. Like, you'll still have access to everything. Just keep in mind it will be timed. Okay, speaking of linear algebra stuff, let's get back to solving. So on Monday and the Friday videos, I introduced this idea of Gauss elimination with back substitution, where we're essentially just thinking about a system of equations as a bunch of vectors, as a linear combination. If I scroll up, we did this wonderful stuff where we can solve a system of equations using substitution, elimination. We can think about our systems graphically as lines or row vectors, and we can also think about them as linear combination or column vectors. And then we can put them together into matrix form. So we talked about all those different ways to look at a system of equations. And then we solved a problem using Gauss elimination, which is essentially just a really beefed up version of the elimination steps that you have learned since your Introduction to Algebra course, I think, whenever you first learned that. So let's start with another problem. So what we do is we are given a system of equations. We write it in augmented form. So here's my augmented form, where it's just where I have my A matrix put next to my B matrix with a line in between. So we can write it in the form of AX equals B. That's completely fine, but you should be comfortable between writing your system of equations as equations, writing it in AX equals B, and also writing it in terms of augmented form. You should be able to go back and forth between them pretty fluidly. And that comes with practice. And then what we do is we have 3 row operations we want to perform. We can multiply a row by a non-zero constant. We can swap rows, so we can exchange rows, which we don't do that often. There are certain situations where we might want to do it, but in general, I encourage you to only swap rows if you absolutely need to. It just keeps things clearer. Different people have different preferences, but that's my preference. Don't swap unless I need to, and I'll explain when you might need to do that. And then the third one is we can do our elimination step, where we can replace a row by adding a row to another row. So when we approach a problem with Gauss elimination, with back substitution, we're going to start typically by putting zeros in our first column. So this number, we don't want to change. That number stays the same. And we want to put a 0 here and a 0 here. So in order to do that, you can use whatever method you want as long as it's valid row operations. I typically always use this first number to make the other one 0. So I'm going to replace row 2 by multiplying row 2 by 2 and adding it to row 1 times 5. So here's my row operation. Row 2 is going to be 2 times row 2 plus 5 times row 1. So there's a couple different ways you can show your work. I am going to show my work by doing my individual multiplications and adding them together. So 5 times row 1 is 10, 25, 15, and shoot. 5 times 28, I got this. Nope, did not do that individually. 5 times 28. Also for your exam, you can have your calculator, so make sure you've got some handy dandy calculator. No, 5 times 28 that you can use. Make sure you type your buttons correctly. And then 140. And then 2 times row 2 would be negative 10, 4, negative 2, and 30, nope, 14. So my answer, row 1 isn't changing, 2, 5, 3, negative 28. I'm using row 1, but I'm not changing row 1. To my knowledge right now, Matt, yes, you can use MATLAB. It will be helpful to check your answers, not necessarily in solving. Row 2 now becomes 10 minus 10, which is 0. 25 minus, or plus 24, 29, 25 plus 4, which is 29. 15 plus negative 2, which is 13. And then 140, that's a negative. Negative 140 plus 14, or negative 126. And then row 3 doesn't change. So 4, 3, 2, negative 23. There we go. I've got my first 0. Woohoo! Now I want to make this 4 a 0. So I'm going to take, once again, I'm using this number. So I'm going to take row 3 and say that it's row 3 minus 2 times row 1. Once again, there's a couple ways you can show your work. Matt, you can prepare for the exam however you want. I'll talk about that in a minute, Matt. So row 3 is going to look like this, 4, 3, 2, negative 23, just row 3 times 1. Row 2, or row 1 times 2 is going to be 4, 5, 3, and negative 56, right? Yes. Okay, so I'm taking row 3 minus row 1. So it's 4 minus 4, 3 minus 5, 2 minus 3, negative 23, minus negative 56. So keep that in mind. So row 1 isn't changing. It's still 2, 5, 3, negative 28. And then row 2 doesn't change, so it's still 0, 29, 13, negative 126. And then in 4 minus 4, which is 0, 3 minus 5, which is negative 2, 2 minus 3, which is negative 1, and then negative 23 minus, nope, that's 6. That's 10. I can do this, I promise. There we go. Negative 7, negative 4, and 33. I'll just follow my work. Okay, so I've got 0 there, 0 there. Yep, I know what you're asking. Like I said, I'll address that in a minute. Now my last step is to make this a 0. So I'm going to say that R3, once again, I'm going to use this number to do it. because I have no other option. I can't use this 5 because I want to maintain the 0 here. So I'm going to use my 29. So I'm going to say R3 is 29 times R3 plus 7 times R2. So notice I'm getting big numbers. You can do fractions. That's completely fine. You can use fractions. I like to use whole numbers. So once again, a couple ways to show your work. I'm going to multiply each row and then add them together separately. So 23 times row 3 is going to be 0. 7 times 23, that would be negative 161. 4 times 29, negative 116. And 33 times 29 is 957. Seem like large numbers. That's okay. We're getting large numbers. And then 7 times row 2. 0. 7 times 29 is 161. I know that because there should be opposites. 13 times 7, 91. And then 13 times negative 126 is a very big number, 1,638. So now my answer, row 1 doesn't change. And then it's going to be this number, this number, 0. Negative 161 plus 161, 0. Negative 116 plus 91, which would be negative 50. Nope. Negative 25. And then negative 1638 plus 957. No! Where did I make my error? Oh, I made an error. Gosh. This is why you always follow your paper. I showed my work differently on my paper, though. I wanted to demonstrate something different. This one. This should be negative 882. There we go. We'll pretend that's right. It should be right. Okay, this is where I stop for Gauss elimination. This here is REF. Row echelon form. I've got my lower triangle of zeros. I can write my system of equations. I can see here negative 25z equals 75. I can easily see that z is negative 3. I can use that number to plug into this equation, use those two numbers to plug in to my first equation. Do that back substitution. So this is where I stop. For Gauss elimination with back substitution. With BS. If I wanted to continue, I can keep doing my row operations and keep what's called reducing this matrix until I end up with identity over here. So let's go ahead and keep doing that. So identity has a lower triangle of zeros and an upper triangle of zeros. So now I also want to make this a 0, this is 0, and this is 0. To do that, I just keep doing my row operations. So I encourage you to start in column 1, make your zeros in column 2, and then move and make your zeros in column 3, or column 2, and then do your zeros in column 3. So I'm going to continue and make this 5 0. So ignore those for now, and I'm going to make this 5 0. Once again, I'm going to use this 29 to do it. So I'm going to say row 1 is going to be 29 times row 1 plus minus 5 times row 2. So here we go. Yep, there it is. So 29 times 2 is going to be, no, stop. 29 times 2 is 58 from row 1. 5 times 29 is going to be 145. 29 times 3 is 87. And 29 times negative 28 is negative 812. Then I'm going to multiply row 2 by 5, or negative 5. Negative 5 times 0 is 0. 29 times negative 5 is negative 145. 13 times negative 5 is negative 65. And 126 times 5 is 630. So now I add them together. So I get 58, 0, 87, minus 65, 22, and then negative 812 plus 630, negative 182. And then row 2 doesn't change, and row 3 doesn't change. At any point in time, you can divide your rows. So let's say I want to clean this one up a little bit. I can divide it by 2, and I can divide this one by 25. So I can make it a little bit neater. So 58 divided by 2, 29, 0, 11, negative 91. Still not the best numbers. But no, we're seeing 29 twice. That's probably a good indicator that we're on the right track. Not every time, but most of the time we give you problems that end up with whole numbers as solutions. Like I said, not every time, but a lot of the times. 0, 0. I'll divide it by negative 25. 1 and negative 3. So now this one's nice and easy, though. I've got my 1 there. Woohoo! So I've got zeros in my first column, zeros in my second column. Now I want zeros over here to get my final upper triangle. Here's my lower triangle of zeros. I want my upper triangle of zeros. And that's off the page. I'll write it here. So I'm going to say row 1 is going to be row 1 minus 11 times row 3. And then I'm going to do these at the same time. So row 2 is going to be row 2 minus 13 times row 3. So I'll show my work this way. It's going to be 29 minus 0, 0 minus 0, 11 minus 11, negative 91 minus or plus 3 times 11 plus 33. It's going to be 0 minus 0, 29 minus 0, 13 minus 13, and then negative 126 plus 3 times 13. 39. So now we can see my answers are 29, 0, 0, 91 minus 33, negative 58, 0, 29, 0, negative 87. That should be the same. Nope, we're good. 0, 0, 1, negative 3. And then my last step would be to divide by 29 for row 1 and row 2. So 1, 0, 0, 58 divided by 29 is negative 2. 0, 1, 0, 87 divided by 29 better be 3. Yep, negative 3. 0, 0, 1, negative 3. So I just got 3 more zeros. Here's my lower triangle that I got from doing just Gauss elimination. And here's my upper triangle of zeros. So when we continue this process through, when we continue from Gauss elimination all the way down to this form, this process is called Gauss-Jordan elimination. And Gauss elimination is great. It's great. We can end here. We can easily solve for our system using back substitution. However, when we continue on into Gauss-Jordan elimination, we end up with something called reduced row echelon form, or RREF. RREF. And the nice thing about this one is if we write our system of equations from this system here, this tells me automatically that z equals negative 3. This one tells me that y equals negative 3, and this one says x equals negative 2. So we can easily see our unknowns are isolated. We have one unknown in each equation and our immediate solution. So this here is going to be our solution. So Gauss-Jordan elimination is the same thing as Gauss elimination with back substitution, except we keep going. We keep going until we have a lower triangle of zeros, an upper triangle of zeros, and then traditionally we have ones along the diagonal. So this matrix over here, you may recall, this side here ends up being identity. So this ends up being our identity matrix. And this is really nice because we can easily see what our solution is. So given a system of equations, there is more than one REF. There's always more than one REF. However, there's only ever one RREF because we end up with identity and our solution. So from Gauss elimination, when we get to REF here, we can solve for our solution using back substitution. However, when we stop at REF, it automatically gives us our solution. So let me go ahead and switch over to MATLAB and show you my algorithm. So for Gauss elimination, this was my algorithm. I showed you guys this at the end of last week. However, I didn't have a chance to run it. So here's my Gauss elimination program. This identifies whether or not we're going to do those row swaps. So I told you that we really don't want to do row swaps unless we have to. At least my preference is you will develop your own preferences. But my preference is to not do row swaps unless I absolutely have to. A reason why you might have to do row operation or might have to do row swaps is if you end up with a 0 in the pivot location. So if you end up with a 0, for example, if you end up with something like this, or this matrix here, if I end up with a 0 here, where I can't use it to create any more zeros. I can't use it to create a 0 here. Okay? So if you end up with a 0 in the pivot location, that's 29, that's when you might have to do a row swap. We will also see in the future with a different algorithm called PLU factorization, then we will also do row swaps. But in general, I encourage you to not do row swaps unless you absolutely have to, unless you end up with a 0 in that pivot location to where you can't do any more reduction to figure out any more zeros. So this is checking to see if the pivot location is a 0, then do the row swap. If not, then here's just perform the elimination step, just like I did. So it says, so here's my row operation, but essentially doing row operation 3, my elimination step. I am multiplying my row by the number in my pivot location, minus or adding, I can't remember how I think I subtracted, the number in front of my, in my row. So just how I came up with my row operations by hand. Okay, this is an algorithmic way, so it's always gonna work. You need to identify the patterns. And if I put in my matrix, so here's my REF, or not my REF, my augmented matrix. And then here's my steps. This is essentially what we did. We made a 0 here, we made a 0 here, and then we made a 0 here. And here's my answer. So this is after performing back substitution. So here's my algorithm for back substitution. For Gauss-Jordan elimination, it's the same thing, more or less, except I don't need to do back substitution. I just find more zeros. So my elimination step is now occurring for every row except for the row with my pivot, except for the row that I'm using to create zeros. There are Gauss-Jordan eliminations, like algorithms all over the internet. You can just Google Gauss-Jordan elimination algorithm, and it'll show you in probably lots of different languages. So I just made one for MATLAB. So let's see this one in action. Gauss-Jordan elimination A. So here we can see it uses fractions. My algorithm's a little bit different. I don't use just whole numbers. I have my row operation using fractions instead. But we can see all of my steps. So it puts a 0 here, then 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 a 0 here, and then it divides everything by this number, divides this row by that number, this row by that number, this row by that number, in order to get my whole numbers. And you can see I get the same solution. So I wrote my own algorithm, and you can see the steps. It literally shows all of my results, what I should get. So Matt asked a question if he can come up with his own algorithm, his own program that shows the steps. That is completely fine for your exam. However, keep in mind the questions aren't going to be as straightforward as calculate or perform Gauss elimination or solve the system of equations. They're going to be worded a little bit different. Your answers aren't going to be as much as solve the system. We might actually tell you use MATLAB to solve the system in order to help you along in your process. You might have variables in your system, so it might not be 3x plus 7y plus 2z. It might be ax plus by plus something else. So you are free to develop as many tools as you want. If you write your own algorithm, that's actually really useful because it's practice. Like, you identify patterns, you identify what you're supposed to be doing. Remember, you need to show your work when you're doing your homework, when you're doing exams. The work that you do shows us that you know what you're doing. So if you just show what the answer is, so like, okay, I know there's supposed to be a 0 here, MATLAB did it for me, that's not telling us that you know what you're doing. You need to show us that, okay, I know I'm supposed to multiply this row by this number and this row by this number. So you need to at least show your work to identify that you know what you're doing. But yeah, so here's my program. So I wrote my own algorithm. MATLAB also has its own Gauss-Jordan elimination algorithm with the RREF function. So if you are asked to, you can always check your solutions. You can say RREF A, put in your augmented matrix, and it will do that algorithm for you. It will give you your result. You just won't be able to see all the steps. So MATLAB, you can always use RREF function in MATLAB, and it will do Gauss-Jordan elimination for you. Okay, let's move on and keep going. Notes. Okay, so Gauss-Jordan elimination and Gauss elimination, both of those can be used to solve a system of equations. We can also use Gauss elimination in order to find the inverse of a matrix. There we go. So we know how to find the inverse of a 2 by 2. The inverse of a 2 by 2 is 1, A inverse is 1 over the determinant of A times A adjoint. Determinant, single numbers. And we learned how to do that back in week 4, whenever it was. This formula still holds for any size matrix. We just need to know how to figure out the determinant and to figure out the adjoint. We are going to get into finding those individually, I believe, next week when we talk about determinants and Cramer's rule and cofactors and all that fun stuff. We can also find the inverse of a matrix in a slightly different way using Gauss-Jordan elimination. So I can write this system of equations in the form of AX equals B. So 2, 3, negative 2, 2, 2, negative 4, negative 4, 0, 5. So AX, write properly, equals B. And let's say the solution to the system is still going to be X equals A inverse times B, or A left divide B. In MATLAB. I can solve the system now using a couple different ways. I can use my substitution, I can use my Gauss elimination, I can use Gauss-Jordan elimination, but now I want to solve it using this method. X equals A inverse B. To find the inverse, we can use this formula. Like I said, we'll learn how to do that next week. I can also use Gauss-Jordan elimination, where what I'm going to do is I'm going to put my A matrix and I'm going to put it next to identity. And now what I'm going to do is I'm going to use Gauss-Jordan elimination until I get identity on this side. And it just so happens that whatever shows up on this side ends up being my inverse. Okay, so let's go ahead and start. I am going to start by putting zeros here and here. Always start in the first column. It's just start in the first column and work your way over. So I'm going to take row 2 and I'm going to say, 2 times row 2 minus 3 times row 1. And then I'm going to say row 3 is going to be row 3 plus row 1. I'm using this number to make this a 0 and this a 0. Notice I'm showing 2 steps at the same time because these 2 row operations don't, they're independent of each other. Notice row 1 doesn't change. I'm using row 1 to eliminate both of them, but I'm not changing row 1. I'm also not using row 2 to eliminate row 3 or row 3 to eliminate row 2. So you can do more than one row operation at a time, just make sure they're independent of each other. When you're doing Gauss-Jordan elimination in order to find the inverse of a matrix, there's a lot of numbers, so make sure you guys don't lose track. Whatever you do on this side, you also need to do on this side. For some obscure reason, I always forget this side when I'm doing these problems, which is very annoying. But there's a couple different ways you can show your work. I'm going to show it this way. So row 1 doesn't change. It's still 2, 2, negative 4, 1, 0, 0. Row 3 is just row 3 plus row 1, so negative 2 plus 2, which is 0, negative 4 plus 2, which is negative 2, 5 plus negative 4, which is 1, 0 plus 1, which is 1, 0 plus 0, which is 0, 1 plus 1, 0, which is 1. So you can see now, row 3 is starting to change on this side. Row 2 is going to be 2 times row 2 minus 3 times row 1. So I'm going to show that up here. I'm going to multiply row 1 by 3. 6, 6, negative 12, 3, 0, 0. And then multiply row 2 by 2. So 6, 4, 0, 0, 2, 0. And I'm going to subtract my two numbers. So it's 6 minus 6, which is 0. 4 minus 6, which is negative 2. 0 minus negative 12, which is positive 12. 0 minus 3, which is negative 3. 2 minus 0, which is 2. And 0 minus 0, which is 0. So notice there's a lot of places where your signs can get messed up. 0 minus 3. You need to have that minus that carries through that negative. 0 minus a negative 12. That becomes a positive 12. So it's just basic math. It's just addition. It's just multiplication. But you need to be careful. You need to show your work because there's a lot of places where you can have one small tiny error that just completely ruins the problem. So it's important that you show your work. You keep track of all of these fun little nuances. So I've got my zeros in my first column. Woohoo, check, done. Now I want to get my zeros in my second column. So I want this to be 0 and this to be 0. This is actually a pretty nice problem. Thus far. So I'm going to take row 1, and I'm going to say row 1 plus row 2. So I'm using this number to do it. Once again, you do not have to do these same row operations. If you notice, I do the same row operations every time. I put a 0 here using this number. I put a 0 here using this number. So those are the same steps I do every time. It's not always guaranteed to work if you end up with a 0. So let's say I ended up with a 0 here. If I ended up with a 0 here, this is an example of where I might do a row swap. I would have to swap these two rows. And that's fine. However, my default is to not do row swaps unless I absolutely have to. So to put a 0 in this location and a 0 in this location, I'm always going to use this number. Whether or not it's convenient. I do the same row operations every time. It just helps me keep track of what I do next. I'm not sitting there analyzing it to think about what's my best option. I look, okay, I know this is a good option. So I'm going to replace row 1 by saying row 1 plus row 2. And then I'm going to replace row 3 by saying row 3 minus row 2. And then I know I can also do more than one row operation at a time. I can do these together because once again, they are separate. So showing my work, or showing my answers, it's going to be, row 1 is going to be 2 plus 0, which is 2, not 0. 2 plus negative 2, which is 0. Negative 4 plus 12, which is 8. 1 plus negative 3, which is negative 2, 0 plus 2, which is 2, 0 plus 0, which is 0. Row 2 does not change. Row 3, 0 minus 0. Negative 2 minus negative 2. 1 minus 12. 1 minus 3. 0 minus 2. 1 minus 0. So we can see here, this side is starting to change. Joey, that's a really good question. No, your X and Y don't change. Because it's not about your row swapping that matters. It's about what your final result looks like on this side. So if we go back to our previous problem, if we go back to this problem with REF, if you do row swaps, as long as you end up with this order, a 1, a 1, and a 1, it really only matters where your ones end up. If you didn't do row swaps, if you didn't do a row swap, you would still get your same answers over here. Because it all matters on where your ones end up. If you ended up with something like this, which this technically wouldn't be REF, but if you ended up with something like this, technically you would still need to do a row swap here. But you can still see your solution. Your solution here says z equals negative 3, y equals negative 3, x equals negative 2. So it's not necessarily about, it's not always x, y, z. It's about where your ones end up over here. So for this one, it's x, z, y, because my one's over here. So this first column is my first unknown, the second column is my second unknown, and this third column is my third unknown. So it really just matters in your final result where your ones are over here. It's a good question. Okay. Okay, so I've got my zeros in my first column, zeros in my second column. Now I want to get zeros in my third column. So I want a 0 here and a 0 here. I can do some cleaning up right now. I could technically divide row 1 by 2. So I get 0, 1, 4, negative 1, 1, 0. That's the only one I can change. I didn't need to do that. But I could have. When you find the inverse using row operations, you're most likely going to end up with fractions. So you're going to run into them eventually. I encourage you to do that last, though. Once again, I prefer to work with whole numbers. I encourage you to work with whole numbers. In general, I think people find them easier to deal with. But I got to get a 0 here and a 0 here. So I'm going to say row 1 is going to be row 1. Whoop, I need to multiply it by a number. I'm going to move this over so we have space. Row 1 is going to be 11 times row 1 plus 4 times row 3. And row 2 is going to be 11 times row 2 plus 12 times row 3. So this one's a little bit harder. So first, 11 times row 1 plus 4 times row 3. So I'm multiplying row 1 by 11, which is 11, 0, 44, negative 11, 11, and 0. Plus 4 times row 3, 0 plus 0, plus negative 44, plus 16, plus negative 8, plus 4. And then for row 2, it's going to be 11 times row 2, 0, negative 22, 1, I should know this, 12 times 11. $132. Negative 33, 22, 0. And then plus 0, plus 0, plus negative 132, plus 12 times 4, 48, plus negative 24, plus 12. I know my handwriting's not the neatest on this tablet, My handwriting is so much neater on paper. So just try to be neat. 0, 0, negative 11, 4, negative 2, 1. Christmas music? Really? Come on, royalty-free music channel. Okay, so when I do this math, I end up with 11, 0, 0. 5, 3, 4. 0, negative 22, right? Yep. 0. Okay, show me my work. 15, negative 2, 12, and then 0, 0, negative 11, 4, negative 2, 1. Okay, there we go. I've almost got identity over here. And we can see over here, I don't have identity anymore. So I'm kind of like switching places. So my last step is to divide row 1 by 11, divide row 2 by negative 22, and divide row 3 by negative 11. So when I do that, I end up with identity on this side, just like I wanted. 5 over 11, 3 over 11, 4 over 11. Negative 15 over 22, negative 2 over 22, nope, positive 2 over 22. 12 over 22, 4 over negative 11, 2 over 11, 1 over 11. So this side here ends up being A inverse. So my A inverse, so A looked like this. It's all the way up there in the corner. A inverse is now this. 5 over 11, 3 over 11, 4 over 11, negative 15 over 22, 1 over 11, 6 over 11, negative 4 over 11, 2 over 11, and 1 over 11. I could technically write this without fractions. I could say 1 over 22 times 10, 6, 8, negative 15, 2, negative 12, negative 8, 4, negative 2. And if you remember our formula is 1 over the determinant of A times A adjoint. So this is a good indicator that that's the determinant of A, and this is our adjoint. So just some fun facts we can pull out. And now I could use this in order to solve my system. Yep, you can always use the inverse to check your inverse. So if I go over to MATLAB, let's see. Yeah, no, okay. There we go, we've got that pulled up. Nope, I want this one. There we go. So if I plug in A into MATLAB, 2, 2, negative 4, 3, 2, 0, negative 2, negative 4, 5. So if that's A, I can do inverse of A. Inverse of the inverse. Yeah, so there's a different way to check that. Let me answer that in a minute. So I can always check my answer with MATLAB. Format, rat. So we can see that I can also see if I do determinant of A. The determinant of A is 22, which is what I pulled out, which is a good indicator. So you can always use MATLAB to check your answers. Another way you can confirm that you have the inverse is to do A times A inverse. So if you do that multiplication, this is the weird birthday song. It's a terrible, terrible selection of random music. 4, negative 4, 0, 5. I'm going to pull out mine 1 over 22. 10, 6, 8. Positive 4. So if I do this multiplication, you should get identity. So 2 times 10, 20 plus 2 times negative 15, minus 30, plus negative 4 times negative 8, plus 32, divided by 22. This here should end up with 1. 20, 10, yep, this is 1. When I do this one, row 1, column 2, nope, wrong one. Row 2, column 1, I should end up with a 0 here, a 0 here, 0, 1, 0, 0, 0, 1. So if you do that multiplication, you should end up with identity over here. We can always do that to check our inverse. On your exam and in your homework, you will have MATLAB, so you can do that as practice, but you can also just check it with MATLAB. So I encourage you guys to check it with it a couple different ways. Sometimes I like to do this with just a quick mental check in a couple locations just to see if I got the right answer. Okay, once we have A inverse then, we know our solution, x equals A inverse times B. So I have 1 over 22. My B vector looked like this, 8, negative 1, negative 12. And I can do this multiplication. 1 over 22, 80 minus 6 minus 94, 92. And 8 times 12 is 80. No, 8 times 12, 96. And then 8 times 15. I'm not going to do that with my hand. Negative 120 minus 2 plus 144. Negative 64 minus 4 plus 24. 80 minus 6 minus 96. Negative 22. Negative 120 minus 2 plus 144. 22. Awesome. I'm getting nice whole numbers. Negative 64 minus 4 plus 24. Woohoo! Negative 44. When I do this multiplication through, I get negative 1, 1, and negative 2. There we go. There's my solution. X equals negative 1, Y equals 1, Z equals negative 2. And that's our material for today, for this week. Gauss elimination, Gauss-Jordan elimination. We can use Gauss elimination, get to REF, get that lower triangle of zeros. REF for Gauss elimination, do our back substitution. Gauss-Jordan elimination, get our lower triangle of zeros and our upper triangle of zeros, and ones along the diagonal. Gives our solution right away. We can also use Gauss-Jordan elimination in order to find the inverse of a matrix. We put A next to identity, do row operations until they're switched. It's just practice. Notice I just did multiplication and addition, or subtraction and division, which are derivatives of multiplication and addition. There's just a lot of places where we can make errors, where we can make mistakes. Okay, that is all I have for today. So on UB Learns, there are additional PDFs showing some additional examples. I will also post the videos. There we go. So here in UB Learns, you can see there are additional examples here. Yes, so Joey, when I did that, it is matrix multiplication. So when we are doing linear algebra, by default, we are doing matrix multiplication. So if I do A times A inverse, it is matrix multiplication. If I do A times B, it is in the matrix multiplication. Yes, A times A inverse, that is matrix multiplication. So the dot product between row 1, column 1, row 2, column 1, row 3, column 1, etc. These processes also apply to bigger than a 3x3. I did 3x3s in class because they're smaller, they're easier to do. I do have 4x4s prepped, but there are more examples written out here. So Gauss-Jordan elimination, you can show, here's more examples. of a 3x3, another 3x3. There's some notes here that we're going to talk about in the future that apply when we get later on. So just keep those in the back of your mind. Do I have any with 4x4s? 3x3, 3x3, 3x3. Where's my 4x4s? I apparently do not have any 4x4 examples. I will put some 4x4 examples together. Yes, you can just upload an M file along with the PDF of your work. That's completely fine, Danny. So there are examples there. I will add in the videos I made last year as well that go over more examples. They're shorter videos. They're quick. So I will put in those links to those videos as well. They're Panopto videos, not YouTube videos, but if you want more examples, you have them. I will put together 4x4 examples as well. I can't believe I don't have any. But the process still applies. Okay, with that, we will stop. If there are any final questions, let me know. You still have the programming project. MATLAB's still here. You can always use MATLAB. Like I said, I wrote my algorithms for solving linear algebra problems one day, and it was so happy and so exciting. I got things to work. I had to figure things out myself. I understand. I understand. Okay, I'm going to jump over to office hours. I will see you guys next week.